Hi, everybody. This is a lesson about various properties of light. You can see the list here of the different things that you are going to learn in this lesson. I have this list at the end too, and you might want to go through the PowerPoint and make sure that you kind of understand each one of these points and see where each of these learning goals or objectives are addressed, within the PowerPoint. Okay. Um, First of all, we need to know what are some of the properties of light. Light's going to travel in a wave. Okay. It is going to have all of these certain properties associated with it. I'm, not the greatest at drawing these things, but oops, hang on a second. Let me get but if this is, for example, a light wave, what do we mean by the wavelength? The wavelength is the distance between two consecutive crests of a wave. So, for example, from here to here, this distance, that is the wavelength. Okay. That should match also from trough to trough because the wave should be traveling at a pretty standard, standard speed. And this would be the same wavelength as what you see up there at the top. The frequency, which is represented by this Greek letter nu, by the way, this is the lowercase n, and wavelength was represented by lambda, which is the lowercase l. You can see the Greek alphabet up there, above the board. But I do have some random things on here. Hold on. I get that sometimes. You guys know that from previous screencasts. Sometimes you just get some random lines. But the lowercase l and the lowercase n, these are just the symbols that they use. So back to frequency. That's how many waves pass a given point per second. Like this wave is going to be traveling in this direction. And if I stand here and I count how many of these peaks go by in a given unit of time, and it's usually measured per second because waves are traveling very fast, however many waves pass that point in a second, that's the frequency. So your unit of that is generally like per seconds, which is the same as 1/seconds or seconds to the -1. This and this are the same thing. But instead of calling it a per second or a second to the -1 or an inverse second, they generally refer to it with this unit, which stands for hertz. Okay. And you may have seen this before if you look on like your radio dial, for example, like, FM 97, 96.9. That is the frequency of that radio station in megahertz in the capital M hertz. So it's 96.9 megahertz or million hertz per second is the frequency of their radio station, the signal that they're pointing out or putting out, excuse me. So the other thing you need to know is that every wave, it has an amplitude, okay? That amplitude, though, does not affect the calculation of the speed of the wave. The speed of the wave is really just the wavelength times the frequency. If you think about it, the wavelength is the number of meters per wave, like how many meters are there from one wave, to the next. The frequency is how many waves there are per second, how many pass per second. And if you multiply those, the waves divide out, and you're left with meters per second, which is a speed. And this is a number that you do need to know, that the speed of light, okay, is 2.998 times 10 to the 8th meters per second. So we're going to use that in quite a few calculations. Okay. So the electromagnetic spectrum. The electromagnetic spectrum is everything all the forms of radiation that move at the speed of light. So everything that you see on the spectrum that I'm going to put up here then moves at that speed, 2.99 times 10 to the 8th meters per second. We can only see just a really tiny segment of that spectrum. We see the visible spectrum and, the rainbow, Roy G. Biv. But there are a lot of different forms of radiation with wavelengths that are longer and wavelengths that are much smaller than what our eyes can see. So it doesn't look like my link is going to work in here. You might want to, I think this would be a good idea. Just one of the things you might want to do is Google the electromagnetic spectrum, or you can look it up in your textbook. Just look it up in the index in the back. I don't have the page number handy because I thought the link would work, but it's not working while I'm screencasting. But you've got like this really tiny, if I could, recreate the spectrum for you. You got this real tiny, sorry. You've got this very tiny segment in the middle that is visible light. And then you have down below there, you have things that are longer wavelength, which means that they're going to be lower frequency. Because remember, the wavelength and the frequency multiplied have to give you the speed of light. If one of them gets longer, a bigger number, the other one's going to have to get smaller. So down on this end with the, like if this is the visible right here in the center, down on this end you have things like radio waves, which can be like 100 meters long from peak to peak. You have things like microwaves and radar waves. You have infrared waves, which are the waves that come out of like a heat lamp, or like if a light bulb's on and you feel the heat being given off. Those are infrared waves. So you have all these things down here that have down here in this area that have longer wavelengths and a lower frequency. None of these are dangerous. The long wavelength and the very low frequency means they have low energy. Okay. This end of the spectrum has a lower energy. Basically means they cannot penetrate your skin. Like this is why it's fine if there's, radio waves traveling through the air, radar waves traveling through the air, microwaves, infrared heat lamps, all those things, like the rays from the sun that keep you warm are in the infrared region. None of those are damaging to your skin. Where we have to worry is when we go in this direction and we get some forms of radiation that move at the speed of light that are shorter wavelengths, and that means they are higher in frequency. And so when you go up to that end, let's see if I can get, hey, I got rid of it. When you go up to that end, you see things like ultraviolet. Beyond the ultraviolet, there's X-rays. I mean, now when we're getting up here, like ultraviolet can burn your skin. X-rays go through your soft tissues, not your more dense tissues like bone. And then you get up here and you get gamma rays, which are really, really short wavelength and very high frequency. And, those are actually, as they travel through the tissue in your body, they can literally cause tissue damage, go through your bones as well. These are the kind of rays that are highly damaging, that are sometimes given off by radioactive elements, and can really cause damage to tissues, etc. So this is a list. There we go. There's the page in the book. Wonderful. So here's a list, okay, and you can always reference that page in the book. This is a list of all the forms of radiation from the longer wavelengths and lower frequency. That means this is the lower energy end of the spectrum, down through and including the things that are shorter wavelength and higher frequency. And that means this is the higher energy end of, the spectrum. And whenever you look at a picture, you're going to be surprised. This visible light, this is but a very teeny tiny sliver of the entire electromagnetic spectrum that moves at the speed of light. So we can only see just the really tiny sliver. You are responsible for knowing these. You don't have to memorize exact wavelengths, but you do kind of want to know which ones are on the safe end and which ones are on the end of higher energy and more damaging rays to your eyes, to your skin, etc. So, in the visible region, there's, of course, if you could take that light and break it apart, you can see a range of wavelengths. This goes from, and again, on page 262, they have this in your book, but this is around on this end, on the red end. These are the longer, wavelengths. Remember over here we have infrared on the longer end. We can't see the infrared, but they are longer wavelengths than the visible red. And then over here, you see how we have violet. These are the shorter, wavelengths. And this is where we get the ultraviolet. We can't see the ultraviolet, but they're even shorter wavelengths than the visible violet that we can see. And you've got a whole range in here. It goes from like the red is around like 700 and some nanometers. And down here in the purple, you're at around like 400 nanometers. So it's a really small little section of the entire electromagnetic spectrum. But this is what is visible to us. Since the red has the longer wavelength, if it passes through like a prism or a diffraction grating or a raindrop, it will bend the furthest. And this is why the red is always on the outside of the rainbow. Or when we look at we're going to look at light through some diffraction gratings in a day or two. And you'll see that the red always bends the farthest from the source, which means, of course, then this violet end down here stays closer to the source. The wavelengths are shorter, and so they don't bend as far, which means that they're always closer to the light source. And once again, and I think most of you do know this, you are responsible for knowing, the colors in the visible spectrum, and that the red is the long wavelength end and the violet is the short. That should be easy to remember, because remember back here, these are the shorter wavelengths. Ultraviolet, violet is towards the shorter end, red is to the longer end. So you do need to make sure you're studying those and are familiar. Now, we have that equation on the previous page, where we know that the speed of light is equal to the wavelength of the light times the frequency. One of the things we're going to do in the lab is we're going to take some light, pass it through grating, or actually a prism, and use a spectrometer to measure the wavelength of the light. And so if we know the wavelength, we can calculate the frequency. Now, remember, the speed of light, is in meters per second. So we need to get this into meters. So hopefully you remember this from your metric and your dimensional analysis. Yep, it's back. That if we go from nanometers to meters, 1 nanometer is equal to 1 times 10 to the negative 9th meters. And so if you multiply that through, you're going to get 6.25 times 10 to the negative 7 meters. That would be the wavelength of this orange light expressed in meters. Solving this for frequency, we got to divide both sides by the wavelength. So frequency is equal to the speed divided by the wavelength. So the speed of light is always the same. Divide that by the wavelength expressed in meters. It has to be so that it can divide out. And then you can see how our meters divide out. We divide, and when you plug this into your calculator, remember how to enter your numbers in scientific notation. Don't hit the times 10 button. Instead, use the EE or the EXP button on your calculator. If you don't get it the first time, definitely ask for help. When you solve this, you should get 4.80, and I'm just keeping 3 significant figures, times 10 to the 14th. And you can see that the unit we're left with is per seconds. Remember that a per second, or a 1/2 is the same thing as a hertz. So our label on this would be hertz. And now we've determined the frequency of the orange light. Moving on, what if you know the frequency? Like there's a radio station, Warm 103. Its broadcast frequency is 103.3 megahertz on the FM dial. So you could calculate the wavelength, like what's the length of the wave that's being generated by, Warm 103. Now, again, the speed of light is in meters per second. So we don't want megahertz, we need hertz. So we're going to have to do a conversion. Again, we need our metric. So, get that. Oops. Okay. So 103.3 hertz. Oops. When I accidentally erased that, I wrote the wrong thing back in there. Give me a second here. Megahertz. Okay. So we want to convert from megahertz to hertz. And you remember your metric, mega. If you have a megahertz, that's 1 times 10 to the 6th hertz. When you multiply through, you should get 1.033 times 10 to the 8th, and that would just be hertz. Now, solving, this time we have to solve for the wavelength. So we're going to divide by the frequency. That way that frequency divides out. Okay. So wavelength is equal to the speed over the frequency. 2.998 times 10 to the 8th meters per second. And the frequency in hertz, which is the same as a per second, 1.033 times 10 to the 8th hertz. We're dividing out our units. Per second and hertz are the same thing. Divide your numbers. And I'm going to keep 4 significant figures. We get 2.902, and the unit is meters. When Warm 103 sends out a signal between each peak in the wave, this is the standard distance. Okay? Does everybody see how you can use frequency to get wavelength or wavelength to get frequency? So if not, make sure you maybe review it again or see me for a little bit of help. These equations, by the way, and I know I had that on one of the earlier slides, this is what is considered the wave model of light. And light is a form of energy that does travel in a wave. Now, I don't know if you remember from the earlier lesson where we were talking about the fact that energy travels in waves but has a particle quality to it. And then the electron is a particle, but it has wave qualities or wave properties. So now we're going to kind of switch to talking about particles of light. Okay. First of all, we need a few definitions. Quantum, that's the minimum amount of energy that can be gained or lost by an atom. Okay. And a photon is a particle of light. Okay. A particle of electromagnetic radiation. It carries the quantum of energy, but it doesn't have any mass. Okay. So photons can have different amounts of energy. And the amount of energy that is gained or lost in an atom is called a quantum, and the photon is the particle that carries that quantum of energy. Now, to calculate how much energy is in a particular photon, we have to use Planck's law. Planck studied the light given off by a lot of different types of matter. For example, like iron always glows red, and did a number of calculations, found that the frequency of the light was always directly proportional to the energy carried by the photon. And the proportionality constant, or Planck's constant, always has this value, okay? 6.626 times 10 to the negative 34 joule seconds per photon. Now, this is the particle model of light, the bundle of energy being the particle. It doesn't have any mass, but it's a bundle of energy. How much energy is in the bundle, in the photon, depends on the frequency multiplied by Planck's constant. So let's do an example problem, okay? CD players. So this is dating me a little bit, okay? I know you guys don't really use CD players anymore, but CD players use lasers that had a red light, and the wavelength was 685 nanometers on that long end of the visible spectrum, up towards 700. So we do need to convert this, remember, to meters. And a nanometer is the same as 1 times 10 to the negative 9 meters. So the nanometers will divide out 6.85 times 10 to the negative 7 meters. So that's the wavelength of the red light in a CD player in meters. Okay? So to get the energy of one photon, we need the frequency. Okay? Now you can do this in 2 steps, or you can sub in and do it in 1. It's up to you. But energy is equal to Planck's constant times the frequency. How do we get frequency? You can look back at that previous slide. It's C divided by the wavelength. You can either use the speed of light and meters to calculate the frequency and then take this answer and plug it in there, or you can substitute in for the frequency C over the wavelength. Either way, either one will work. So if we want to calculate the energy per photon, get my random lines in under control here. The energy per photon, we have Planck's constant, 6.626 times, times 10 to the negative 34, and this is a joule second, per photon. And gosh, I hate when it does that, but it does that to me a lot. Okay. So photon. That you can take by speed of light divided by the wavelength. Speed of light, 2.998 times 10 to the 8th meters per second. And divided by the wavelength, 6.85 times 10. Wanted to write that. Sorry. I revert back sometimes. Times 10 to the negative 7 meters. Now, if we go through here and, divide out some of these units, the meters divide out, seconds will divide out with per seconds, and you are left with the joules in a single photon. So we've got to get that answer. And so let me see. If you did it in 2 steps, where you got the frequency and then plugged the frequency in, you would get 2.90 times 10 to the negative 19th. And I want to see if this, because sometimes if you do it in all in 1 step or in 2 steps, it gives you, and no, still gives you the answer that you get. And I'm going to just put the answer down here. The energy is 2.90 times 10 to the negative 19, and the label is joule per photon. Each photon carries that many joules. Now, that's not a lot, is it? That's a really small number. But here's the thing, like a stream of light in a CD player, it's going to have trillions and trillions and trillions of photons, okay? In fact, what we really want to know here is for each mole of photons, how much energy would that be? Now, if you were going to do this per mole, okay, you know from our previous unit that a mole means you always have this many of something. So this would be the number of photons in 1 mole. We can take that times our answer that we got per photon, 2.90 times 10 to the negative 19, because that is the number of joules in 1 photon. And when you multiply those, do you see what divides out? The photons divide out, and you're left with joules per mole. How many joules would be carried by each mole of photons? And then there's ways to calculate how many moles of photons you get in a certain situation. So once you know how many joules per mole, then you can multiply that by the number of moles. So in this one, let me see. When we multiply those, I actually get 175,000 joules per mole. Okay, so that's a mole of photons. And let me get a color that's a little easier to see. So if I want to convert that into kilojoules, you really got to watch that on WebAssign. Some of those, you know, are like, they ask for the number of kilojoules. Remember that there is 1,000 joules in a kilojoule, because kilo means 1,000. So when that divides out, you would get 175 kilojoules per. I couldn't make it through without one more of those random lines. You would get 175 kilojoules for every mole. Okay? So this particular question just says, what is the energy? So it's not specific to a unit. Either one of these answers would be just fine. But you got to watch it on WebAssign. Do they ask for the answer in joules, or do they ask for it in kilojoules? You might need to do a little converting. You see where all your metrics going to really come in handy. Like we have nano with the wavelengths, we have mega with the hertz, the frequencies. If you look in your microwave, go home tonight, look in your microwave, you might see kilohertz. So the AM dial on a radio is in kilohertz. You've got the joules to kilojoules here. So, you know, kilo, mega, nano, you need to know a number of these different, these different prefixes to be able to successfully do these questions. Okay. Now, how does this all tie in with the atom then? Okay. So another definition that we need, what's a standing wave? Okay. A standing wave is something that has like 2 or more points of no movement. Like I always think about a harp. If I've got a string that is, this length, there are only certain wavelengths. Like when I pluck that string, It can have this wavelength. It could have this. It could have this, because these ends are attached. It has to be a point of no movement. So there's only certain wavelengths for waves that will fit into that length. Well, atoms are kind of similar. In an atom, remember we determined the other day that electrons travel in waves around the nucleus. And that was the basis of the quantum mechanical model of the atom. And again, I'm terrible at drawing, but oops, and there I even pulled up a menu. But so if I've got an electron traveling in a wave, it has to, there are only certain wavelengths, because it has to come back and meet itself without any overlap and follow the same path. Now, it's rough. It's supposed to be on top of itself, following exactly the same path. But what happens is if it comes around, like let's say, it comes around and it doesn't meet itself, it will start to cancel itself. This is not an allowable wavelength, because you'll see the peaks and the valleys, they cancel each other. That is not a permissible wavelength for that distance from the nucleus. Every energy level in the Bohr atom, and I know this is rough, but every energy level in the Bohr atom is a certain distance from the nucleus, and the electron, as it travels in waves, only has certain wavelengths that will come around and meet itself without any overlap. So when Schrodinger wrote the quantum mechanical equations, like this was a stipulation or a requirement as, part of the wave function. And so each wave function had to be a standing wave. So only certain wavelengths would fit in there to satisfy the equation, because it has to come back and meet itself where it started. Okay. As a result, there were only certain answers for each level that satisfied the equation. And that's going to be our next lesson then. Well, like, okay, level 1. What are the allowable sublevels? What are the allowable orbitals? Remember, each wave described a region in space where the electron was most likely to be found. That's an orbital. Orbitals combine to make sublevels. Some sublevels combine to create a level. But each level is a different distance from the nucleus, so each level had its unique answer set. Each level had its unique number of sublevels and orbitals that were able to satisfy the equation. And that's why, like, level 1 can only hold 2 electrons, because there's only one orbital that satisfies the equation. But level 2 can hold 8 electrons, because there's 4 different orbitals that actually satisfy the equation. And we're going to learn those. We're going to learn those in a future lesson on electron configurations and orbital diagrams. But what it means really, though, is that when, Bohr was looking at these spectra, and remember, he was looking at the hydrogen spectrum and calculating where the energy levels were for the hydrogen atom. He was treating the electron as a particle. And then Schrodinger said, no, we got to treat it as a wave. And remember when the, hold on, why won't this draw on there? You know what? Hold on. I think I'm getting, because I have it dark like the frame is, I'm actually going off the frame there and I didn't realize it. So give me a second. So this, this is the Bohr idea that there are, energy levels. And remember that an electron can move up if it absorbs energy from an outside source. We're going to use electricity, but there are some elements that just fire is enough. Like when you see fireworks, the fire, the energy there is enough to make some of the electrons jump to a higher energy level. The ones that I'm going to show you in class are gases. So fire is not enough. We need to use electricity. But we're going to cause electrons to absorb energy and jump up to a higher energy level. And then when they jump back down, okay, they will give off a quantum of energy in the form of a photon. And it'll be the difference between, like, if this is the energy of level 2 and this is the energy of level 1, E2 minus E1 is going to give you, I don't know how I did that, okay, the energy of the photon. Well, we can't measure the energy of the photon, but what we can measure is the wavelength of the light that's associated with it. And once we know the wavelength of the light, go back to these equations. Once we know the wavelength, look, all we need to know is the wavelength, and we can come up with the energy and how many kilojoules per mole represents. So we are in lab going to be able to pass the light that's given off from these electrified elements, pass it through a spec, break it into the visible spectrum, and we actually have a little scale in there that we can read to to measure the wavelengths. So we'll be doing that in lab. Each element has a unique set of wavelengths that it gives off, because each element has different levels, sublevels, etc., that are occupied by electrons. So each element has this unique set of wavelengths, and you'll get to see that in some of the demos. You get the emission of light when it goes from the excited state back down to the ground state. So like on my circles, that's when it goes back down is when it gives off light. And it's unique for every element, so it can be used to identify. I don't know if you ever wonder, like, how do they know that the sun is made of hydrogen and helium? Well, they looked at the light from the sun, broke it down into its spectra, and matched up the spectral lines, the wavelengths, with wavelengths produced by hydrogen and helium in their atomic emission spectrum. How do we know that there's, what's the composition of a star? We've looked at the light from the star, passed it through a spec, way fancier than what we have, measured the wavelengths, and matched them up to known atomic emission spectra. There's a poster on the wall in the classroom. You can go look. There's the spectra for, 8 to 10 different elements on there, and you can see they're all different. You can look up spectra on the internet. You can put in atomic emission spectrum and for any element and get its spectrum, and they're all unique. For every element, there's a different set of spectral lines, and so it's like a fingerprint, and it can be used for identification. So we'll do that in the lab. The last thing we have to go over, okay, is something I kind of alluded to the other day. It's that I know when, Bohr did his energy levels, that, he likened it to the rungs of a ladder, but the rungs of a ladder would be standard. Like if they're 6 inches apart, they're all going to be 6 inches apart. And you can look at this in the book. I don't expect you to do the calculations or anything, but when you have the nucleus, okay, and remember, I cannot draw this to scale because if my nucleus was that big, the first electron would be, if you're sitting in the classroom, it'd be out by Winridge Farm. But as you move out from the nucleus, okay, man, I hate those randoms. Sorry. Okay, hold on. So as you move out, and I'll try to keep this as neat as possible, the levels get closer together. So when I draw level 3, I'm purposely drawing it closer to level 2 than level 2 was to level 1. The energy difference The energy difference from 3 to 2 is smaller than from 2 to 1. Like if I had the energy difference between 2 and 1, that's going to be bigger than the difference between 3 and 2. Do you see that? Why? Because level 2 and level 3 are closer together. Okay? And so, if you keep going out, level 4, this is really hard to draw, is even closer to level 3 than 3 was to 2. And then level 5, is even closer, and level 6. As you move away from the nucleus, okay, as you move away, the energy levels, missed that. As you move away, the energy levels, jeez, I'm really striking out, aren't I? Because what I really wanted to do was highlight that. Am I going to get it this time? Yay. As you move away from the nucleus, the energy levels get closer together. Okay? So you can use that little tidbit of knowledge there to help you out with answering questions like this. I'm not going to have you use the Rydberg equation. You can look at it in the book, and it's a little confusing. And you might use that. In fact, I know you will use that in AP Chem. But in Honors Chem, we don't have you calculate the exact amount of energy, but we might have you compare. Okay? So here it says which electron jump is going to absorb the most energy. This is saying, like when it says n equals 1 to n equals 3, that's like it's going to jump from level 1 out to level 3. That's n equals 1 to n equals 3. 3 to 4 would just be from 3 to 4. Do you see how that's a smaller jump? Now, I'm not even going to look at these two. Why am I not even going to look at those two? Do you see that? They're coming down. When an electron jumps closer to the nucleus, it gives off, these give off energy. And the question specifies absorb. And you can see which one's a bigger jump. 1 to 3 is a way bigger jump than 3 to 4. So which one is going to absorb the most energy? An electron that's jumping from 1 to 3 is going to absorb the most energy. Get a different color to do this next one. Which one's going to emit light of the longest wavelength? Oh boy. Okay. This question is challenging. So we've got to think about this a minute. And I put that on there for a purpose. So remember that energy is equal to Planck's constant times the frequency, and the speed is equal to the wavelength times the frequency. So if we want the longest wavelength, we want this number to be big. That means the frequency is going to be low because they equal a constant when you take their product. So they're inverses. As the frequency drops, the energy is going to drop because they are directly proportional. Do you see that? This is a constant, a proportionality constant. Now, once again, I can kind of eliminate some of these. Like, I'm going to get rid of the 1 to 5. Why? Because it's jumping up, and that absorbs light, and I need something that emits it. See another one there that we can eliminate? It's definitely not it. Yeah, 1 to 2. That's going to absorb light because that's jumping from 1 to 2. Okay? So which one is going to emit the longest wavelength? We're looking for the smallest energy jump. Remember this? Look right there. We need the energy to be the smallest. Which one's smallest? 5 to 4 or 5 to 2? 5 to 4 is just going to be this tiny little jump. 5 to 2 is a much bigger jump. We want the lowest energy difference out of all the choices. Now, there are some in the book for you to practice like this. There are some on a worksheet. I'm going to be giving you a worksheet to practice. And there are certainly some on WebAssign, okay? And with all of them, you really have to think about which levels. Is it going out because it's absorbing light, or is it jumping down because it's giving off? And which levels, because as you go out, those levels get, much closer together. So think about this list right here. Identify the wavelength and the frequency, and then calculate those using the speed of light. Remember, we had C is equal to the wavelength times the frequency, and we used that. List the forms of energy on the electromagnetic spectrum from the longest to the shortest wavelength. So the long end is like radio waves, radar waves, microwaves, infrared, then visible. Then you go to the real short ones that are damaging, like UV can damage your eyes. That's why you want sunglasses with UV. And then ultraviolet rays cause your skin to burn, so you wear sunscreen. And then gamma rays, which are the shortest wavelength and the most damaging, those are given off by radioactive elements. We use the frequency and Planck's constant to calculate the energy of a single photon and then multiply it by Avogadro's number to get a mole of photons. How does the atomic emission spectrum identify an element? Remember that it is a unique set of wavelengths produced when an electron in the excited state moves back to the ground state. And since it's unique, it can be used like a fingerprint to identify the element. And then being able to compare wavelengths, frequencies, and energies of the electron transitions between the levels. As they're going away from the nucleus, energy is absorbed. As you move towards the nucleus, energy is emitted. And remember that energy and frequency are directly related. So then the wavelength always moves in the opposite direction. If it's a big energy jump, it's going to have a high frequency and a really short wavelength. Gamma rays. If the energy is low, if we went the opposite way, if the energy was low, then the frequency would be low and the wavelength would be long, like radio waves. Okay. Now, electrons don't give off radio waves and gamma rays because those are the two extremes on the outside of the electromagnetic spectrum. But when electrons move around within the energy levels, they give off a lot of frequencies in the visible range, and they do give off some frequencies and wavelengths in the ultraviolet and the infrared range. Okay, and you'll see that when you do the reading. But hopefully, you remember where you learned all of these things. You can review the screencast as many times as you want. Okay, and so hopefully that's something that will help you out with that. So hopefully this has helped. Okay. Let me see. All right. I just got to figure out how to stop sharing. There we go. It's been a while. All right. I hope that's helped, and enjoy the sunset.